Alright, welcome back guys. We talked about what rational functions were, how to find their domains, how to find their vertical and horizontal asymptotes, and you shouldn't have to find their oblique asymptotes. Okay. And the last thing we're going to do is kind of put all this information together and see what the graph of some of these rational functions look like. Okay. This is just a brief synopsis of kind of what we talked about. So you can read through this. Also note that these asymptotes that we talked about, guys, these are not part of the graph of the function. Okay. Now when I graph them in Desmos, I do put in those lines, but that's just to show you where those asymptotes are. Those asymptotes are just imaginary. So anyway, all right, well, there's a last couple of things I need to tell you before we embark on this is we also are going to want to know where the x and the y intercepts are, okay, to get an accurate graph. And so you remember to find the y-intercept, you just plug 0 into the function, or in other words, let x be 0, because that's what's characteristic of a point on the y-axis, is that the x is 0. So you just plug 0 into the function, and then to find the x-intercepts, or the zeros, in other words, you're going to set the function equal to 0 and solve for x. But because the function will only be 0 whenever the numerator is 0, all you really have to do is set the numerator equal to 0, okay, for these rational functions. All right, and then this is just a 5-step process to kind of go through that. All right, so let's take a look at a couple examples. So example 4, we want to list the domain, the x and the y-intercepts of the function, and we want to graph it. Okay, and it says be sure to label all asymptotes, so we're going to need to find those asymptotes as well. All right. Well, let me get my, just a second, guys. All right. Well, I like to start by finding the domain. But before I do that, I'm going to make sure that this function is in simplified form. Okay, so I'm going to try to factor both of these polynomials. So they're both quadratic, so they'll be relatively easy to factor. The one on top is going to give you 2 binomial factors. Factors of -6 that when combined give us a 1 would be 3 and -2. Okay, so that's the way this one's going to factor. And then the quadratic on the bottom is going to factor similarly to binomials. And then we need to find factors of 3 that sum to 4. Well, 3 times 1 and 3 plus 1 is 4. Okay. All right. Okay. Now, you'll notice there is a common factor here that we're going to be able to cancel. Okay. However, we don't need to worry about this until we first find the domain. So the domain comes from the denominator before you simplify anything. So I've already got the denominator factored. So to find the domain, I'm going to set each of those factors equal to 0. And I'm going to get x is equal to -3 and -1. Okay, so those are my 2 exclusions. So the domain is going to be all real numbers except for those 2. And we can say the domain is all values of x such that x, I'm just going to put, is real, and x cannot be equal to -1 and 3. And notice again how I put these in order. Okay, I put the smaller exclusion first and the larger exclusion second. And then what I like to do is, since I'm already kind of working with my denominator, I like to find the vertical asymptotes next. Okay, well, those come from the denominator as well. However, that's after your function has been simplified. Okay, so when you actually simplify your function, there's a pair of common factors. Now, most of the functions you guys are going to come across probably will not be simplifiable, but you will see one or two that you can. And so we're only going to actually have one vertical asymptote, because after we simplify it, then this is our function. Okay, so I only have one factor down there now, and when I set that equal to 0, I get x is equal to -1. So that is my vertical asymptote. So even though I have two exclusions in my domain, there's only going to be one vertical asymptote. And we're going to talk a little bit more about this here in a second. Now, as far as my horizontal asymptote goes, I need to look at the degree of these two polynomials. Well, these are both quadratics, so the degree is the same. Okay, so whenever the degree of your rational function, or the polynomials in your rational function, are equal, then it's just the ratio of these two leading coefficients. So the horizontal asymptote will be y is equal to 1 over 1, which is 1. So y is equal to 1. That is our horizontal asymptote. Okay. All right. And then we still need to find the y-intercept and the zeros, or the x-intercepts, in other words. The y-intercept just comes from finding f of 0. Okay. So typically this, a lot of these terms are going to cancel, right? All these x terms will just turn into zeros. And so we'll be left with a -6 over 3. -6 over 3, which is equal to whoops, I got a little ahead of myself. That is -6 over 3, but that's actually equal to -2. So the y-intercept is the point 0, -2. Okay. All right. Now the last thing I need to find are my zeros, or my x-intercepts. We're gonna say x-intercepts because that's what we're asked for. Because remember, a 0 is just a value for x. An x-intercept is an actual point. Okay, so you have to express it as an ordered pair, similar to how I express this y-intercept as a point. All right. Well, the x-intercepts, or well, just look at it like you're finding the zeros first. Okay, they're going to come from values of x that make the numerator 0. Okay. Okay, so I'm going to take my numerator, and I'm going to set it equal to 0, and I'm going to solve it for x. However, I'm not taking my original numerator. I'm taking what's left after I simplified it. Okay, so the only thing I have left in my numerator now is x minus 2. So when I set that equal to 0, I get x is equal to 2. So 2 on the x-axis is where this function will cross. And as an ordered pair, it would be 2, 0. Okay, your x-coordinate is 2. All right. Now we can I'll draw a rough sketch here. Kind of put this information in here, and then we'll graph it in Desmos. Okay, something like that. And what I like to do first are, I like to draw in my vertical and my horizontal asymptotes. So I've got one at x equals -1. I'm going to get a different color here to draw this in. Green I don't think is a good choice. Well, this one. Okay, so x equals -1 is right here. And then I have a horizontal asymptote at y equals 1. So y equals 1 will be this horizontal line. Okay. And then what I like to do is go ahead and plot my x and y intercepts. Well, the y-intercept is at -2, 0, -2. It's going to be right here. And the only x-intercept is at 2, 0. So it is right here. Okay. So remember how lots of times these asymptotes kind of partition our function. And so my guess is that since these 2 points are down here in this fourth quadrant, one piece of my function is going to be in that area. And then my other piece is either going to be, it's definitely going to be on the left side of this vertical asymptote, but it's going to be either above or below this horizontal asymptote. Okay. So what I might recommend that you do now, guys, is just go ahead and graph it yourself. Okay. Technically, to figure out where it's going to be, you would pick a value of x in this area, plug it into your function, see what that y-coordinate is. Wherever that point is, that's where your other piece of your rational function will be located. I think this one's actually going to be down here. And my guess would be that it is going to look something like this. We'll verify this in Desmos here in just a minute. I think this is the way the function's going to look. And furthermore, you may say, well, it looks like it's crossing the y-axis right here. Or not the y, but the x-axis. And we found the x-intercepts, and there was only one. So, you know, what's going on right here? Well, if you notice, look back up at the numerator here. This other factor, if I had set that equal to 0, I would have got -3. So I would have got this point right here. But think back to the domain. -3 is not in the domain of this function. Okay, that's why we divide these out. We just work with what's left. So if -3 is not in the domain of the function actually has a hole in it right there. And that hole, guys, is called a removable discontinuity. And when you see graphs in your homework, you'll see something like that. And there'll be a little hole drawn in there. That just means that it looks like the function's going to go through that point, but it actually doesn't. That point has been taken out. It's not part of the graph. Okay. So this is a little bit tricky. And usually, well, you'll end up with a hole in your function whenever there is a common factor here. That typically is when you're going to end up with a hole like that. All right, well, let's graph this function in Desmos real quick. See how close we got. Okay, that is my numerator. I'm going to keep that in parentheses. I'm going to divide it by that other quadratic function, x squared plus 4x plus 3. Okay. And look, this is similar to what we got, isn't it? Okay. Or wait a minute. No, it's not, because this piece is actually on the... This is kind of weird. I'll just double check here. No, that's right. So in my graphing over here, I assumed incorrectly that other piece. So that's why you want to graph it first, okay? Or that other piece is actually up here. Whoops, I want to keep blue there. The other piece is in this area, okay? But there is still a removable discontinuity at -3. Okay, so wherever the function crosses x at -3, there is an infinitely small hole there because that point has been taken out. Okay. Now you're not going to see this when you graph the function. See, you could zoom in. So here's -3. So you could zoom into this point as much as you want, but you're never going to see a hole in it right here. It's this point right here. But notice, well, let me refresh this. Well, it took out my function. Great. What is this? Plus x minus 6 and divided by x squared plus 4x plus 3. Okay, here we go. Yeah, so right here at -3, you can zoom in. Now I will click right here, but notice, actually, look right there. When I click at -3, what does it say that y-coordinate is? Undefined. Function doesn't have a value when x is -3. But like I said, you can zoom in here forever and you'll never see, you're never going to see a hole. Okay, but if you click right there, you can see that it is undefined for that value. So anyway, Alright, well, let's look at the last one then. Example 5. We're going to do the same thing with example 5. It says list the domain, the x and y intercepts, determine all asymptotes, and then graph the function. Okay, so again, the first thing I'm going to do is try to factor this function. Well, the numerator is quadratic, but it doesn't have 3 terms. So the only thing I can do is pull an x out. So if I take out an x, let me get back to blue here. If I take out an x, then I'll have an x plus 4 left over. Okay. Now in the denominator, this is a cubic polynomial. And I can first pull out an x because all 3 of these terms have x's. Okay. So if I were to take out an x, then I would have 3x squared minus 11x minus 4. And then I would need to try to factor this quadratic right here. Well, because there's a 3 in front of that x squared, I'm going to have to factor it using the AC method, unfortunately. Okay, so I'm going to kind of come over here to do this. So a little bit more practice using the AC method. Well, A times C, okay, will give us -12. So we're searching for factors of -12 that when combined give us -11. Well, they will be -12 times 1. And so then what I do, if you recall, I leave my first term the same, my last term the same, but I rename this middle term using these two. Okay, and they each get an x, by the way. So minus 12x plus 1x. And then we group them up. This is what we refer to as factor by grouping again. Okay, you want to put a plus sign between your two groups. and you take out a greatest common factor from each of these. So in these first two terms, I can pull out an x and a 3. So I can take out a 3x. That'll leave me with an x and a minus 4, I believe. And then in this one here, guys, you can already see what I have left. X minus 4 already matches. So that's an indication that the only thing I want to take out is a 1. Because factoring out a 1 will not change anything. And so now, because I have x minus 4 common to both of those terms, I factor it out, and that leaves me 3x plus 1. Okay? And so that's the rest of the factorization right here. 3x plus 1 times x minus 4. All right. Well, we finally got everything factored, so now I can work on my domain. Okay. Well, because the denominator is now in factored form, I just take all these factors, set them equal to 0. So that one is done. The 3x plus 1, you're going to have to subtract 1 and divide by 3, and you'll get x is equal to negative 1/3. And then the x minus 4, you're going to get x is equal to 4. So these are 3 exclusions here. So the domain is going to be all values of x such that x is a real number and x cannot be equal to any of those 3 values. Okay, and again, I ordered them. Alright, so that's the domain. Now, let's move on to finding the vertical asymptote, or asymptotes. Well, you got to make sure your function is simplified again. Well, we have a pair of common factors here. Now, I made sure that both of these examples had that in there for you, but a lot of your problems in the homework, when you factor them, nothing's going to cancel, okay? But I just wanted you to be well prepared in case you did have to, you need to factor and simplify. Okay, so what do we have left in the denominator? Well, just these 2 factors. So we're only going to have 2 vertical asymptotes, similar to the last one. The last one we had 2 restrictions from the domain, but we only had 1 vertical asymptote because the other value of x had a hole associated with it in the function. Alright, so if I take those other 2 factors, set equal to 0, then I'm going to get x is equal to negative 1/3 and x is equal to 4. These are my 2 vertical asymptotes. Okay. Now for my horizontal asymptote, we've got to compare the degrees again. Well, I've got a 2nd degree polynomial on top and a 3rd degree polynomial on bottom. So the degree of my polynomial on top is smaller or less than the degree of the polynomial in the denominator. And so whenever that's the case, your horizontal asymptote is the x-axis, okay, which is y equals 0. Okay. All right, now let's find the y-intercept. This has one. The reason I said if it has one is because I know that 0 is not in the domain. So when I plug 0 into this function, it's going to become undefined. In fact, you can see this. All these terms will turn into 0, and you get 0 over 0. Well, that is not a defined mathematical operation, okay? And so consequently, there is no y-intercept for this function. Now, as far as the x-intercepts go, again, you're only going to take whatever's left from your numerator and set equal to 0. Okay, so you're going to get negative 4, but the x-intercept, again, remember, is a point, so its coordinates would be negative 4, comma, 0. So there's only one x-intercept. And there is no y-intercept. Okay. Anytime you have a vertical asymptote that's x equals 0, or if you have a function in which 0 is excluded from the domain, you can't have a y-intercept. It's impossible. Alright, so now we'll draw a little sketch and then we'll check this. Alright. Okay, so I'm going to sketch in my vertical asymptotes first. I've got one at negative 1/3 and one at 4. So negative 1/3 is a little bit, it's a third of the way from 0 to negative 1 on the x-axis. Okay, so like that. And then my other one occurs at 4, so over here. And then my horizontal asymptote is y equals 0, so it's right on top of the x-axis. So I kind of sketch that in. Okay. So notice, with these two vertical asymptotes, we actually have 6 different regions here. Alright, well, there is no y-intercept, okay? And there's only one x-intercept, and it's at negative 4. So let's plot that one. Y-intercept, or excuse me, the x-intercept is at negative 4, so it's right there. Alright. Well, this doesn't tell me a whole lot about how this function's behaving. Okay. I will say this. These two outer regions, whatever the function is doing, well, actually, I can't say that because I'm not sure. So to check, guys, again, go ahead and graph it. This time, though, I'm going to use this calculator, because I want to make sure if you're using one of these, you're inputting it correctly. So for y, when you go to y equals, make sure that you keep that function or that polynomial on top in parentheses. Whoops, what am I doing? Okay, so x squared plus 4x, close those parentheses, and we'll divide this, and then open the parentheses, and then plug in the rest of your function. 3x cubed minus 11x squared minus 4x, and then close those parentheses. A lot of times students will make a mistake by not keeping these polynomials in parentheses. Okay, so now I'm going to hit the graph key, and this will give me an idea of how this function is going to look. So see, it's sketching the function in around these asymptotes. So, you know, we could zoom in if we want, but I can see enough that evidently most of this function is in this region here on the leftmost. But it actually crosses the x-axis right here. And then I guess it stays strictly below the x-axis as x goes to negative infinity. And then the piece in the middle, the function is completely below the x-axis, so it's doing this, okay. And then finally, the rightmost piece is above the x-axis, okay, so it's looking something like this. Alright, now again I want to point something out to you. There was no vertical asymptote that corresponded to the exclusion 0. But you can see the way I drew this in, it looks like it's crossing the y-axis. Even if, let's go to our graphing calculator here, and I'm going to zoom in. So see right there, it looks like it's crossing the y-axis. So why isn't there a y-intercept? Well, because 0 is not in the domain of this function. So there's actually a hole right there where the function would have crossed the y-axis. There's a hole, okay? Now Desmos would have been a better graphing utility to see this. You could actually, put your cursor right on that point where that y-intercept would have been, click on it, and then you'll see that that's where the function's undefined. So that's why we have a hole in this one. So I've given you a couple examples of rational functions that have those removable discontinuities in them. But I think in your homework you're not going to see that very often. Alright, well anyway, now remember too guys, when we study these functions we are studying them from a theoretical approach. If we were to use them in a more practical application, then we would probably be restricting the domain. So, like I said, a lot of functions are functions of time, or units produced by a business or a factory. So if that were the case, then I would only be considering, the right-hand side of a function, or just a specific part of the function. Okay, so I just wanted to point that out. All right, well, I'll let you go.